All right, let's talk a little bit about the first part since I did walk again. I did get a couple questions. That's good. I've drawn an extra picture in here. It's not uncommon for the AP exam to leave out intermediate steps and expect you to know what happened in the middle. So there was something that happened in the middle here that was unpictured, and that's the fact that the rod swung down, and there was a moment just before the collision where the rod had a maximum rotational speed. And that's also when all the energy was transformed from gravitational potential into kinetic. You need that moment because that moment exists before the collision. The collision part of the problem takes place directly after this. These are instantaneous moments. So in this moment, we started with gravitational potential energy because the rod's center of mass is going to be changing height. Now, there's something here that I can convey to you, but you may not understand it right away, which is why you take notes and study. How do I know to use energy here and not forces or something else? We have other things at our disposal, and I told you to use energy at the start of this to get you started. But how would you know? Like on your test, it can have anything on it now. We're at the end game of this year. So your tests aren't going to be just one thing. They're going to have all the things. And the reason why I know to use energy here is because we're looking for a velocity. There's going to be a collision, and collisions are always about momentum, and momentum is about velocity. So I need to know how fast the bar is swinging. Energy is almost always the fastest way to get to a velocity. Almost. There are situations in which we can't use energy, but in a lot of situations we can, and this is one of them. So in this particular situation, the bar has gravitational potential energy before it swings down. I know that because the center of mass of the bar changes. And that's something that a few of you forgot about, that we don't talk about the entire length of the rod. We talk about how much the center of mass of the rod changed height. So the center of mass didn't drop 1.5 meters. The center of mass dropped 0.75 meters. Now, once we understand that, we can set that up as conservation of energy with the original amount of energy being equal to mgh. Any question about that? Now, it's actually mg L over 2, if I want to look at it this way. I kind of like doing stuff in symbols first and putting the numbers in later, because oftentimes what you have to do when you put your numbers in later is easier. Now, when it's at the bottom, what kind of energy does it have? Why isn't it translational kinetic? Right. So we have a fixed axis of rotation, therefore it can only be rotational kinetic energy. It's worth putting into your notes too, because a few people had 1/2 mv squared in there. And although I can understand that because the center of mass is moving, the center of mass moving isn't enough of a criteria for it to have translational kinetic energy. It also can't have a fixed pivot point. Both of those have to be true in order to have translational kinetic energy, right? Motion of the center of mass and no fixed pivot point. So this will have to equal 1/2 I omega squared. All right. So luckily, many of you went the extra mile and knew that the moment of inertia about the end of a rod was 1/3 ml squared. Good job. Now there's stuff we can cancel out here, correct? So we can get rid of the 2, we can get rid of one of the L's, we can get rid of the M. That just simplifies our calculator work later. And I like doing it that way because you're more likely to have a problem in which you have to use symbols than you are numbers, but we have numerical information here we can plug in at the end. And it looks like omega squared is going to be equal to 3g over L. And this is going to be 4.5 radians per second. So, okay, that was not new information. I would have expected 100% of you to be able to do that portion of the problem. This part requires new information. And this is a collision, and not a particularly elastic collision, too. So there will be some follow-up questions here in a minute. but in this collision, momentum is conserved. But this is a weird one because we don't have linear momentum, we have angular momentum of the rod being translated into linear momentum in the ball. But we have to consider the ball's angular momentum relative to the pivot point. It's a weird idea and it takes a little getting used to. But this is how we figure out the velocity of the ball, because the ball is going to leave after the collision with an angular velocity relative to the rod. So we're going to compare the angular velocity of the angular momentum of the rod with the angular momentum of the ball. Now, just so you guys know, there are plenty of examples of this question where the rod keeps going, and therefore the rod also has angular momentum after the collision. So there are levels of complication to this problem. I'm presenting the least complicated version, but there are other ways this problem can be presented, okay? So I just want to make sure we understand that if the bar continues to swing upwards, you'll probably have to do another conservation of energy question to figure out how fast the bar is moving after the collision. It's not an unusual question. And we had one like it first semester, but it wasn't an object like this. It was a box on the end of a string hitting something and then continuing after the collision. And if you recall, the thing that was here was at the edge of a table, and it went on to become a projectile. Remember all these little things they can add to these questions? So when I say that we're looking at the base level problem here, I kind of mean it. This is the base level problem. This part's not particularly hard if you know what the parts are. Now the left side's going to be I times omega, because that's the angular momentum of a rotating object. But the right side, because the bar is stopped, it has no more angular momentum, but the ball keeps going. The ball has angular momentum relative to the pivot, and it's calculated as r times p times the sine of an angle. And this value should stay constant with the ball as long as it's not experiencing an external force. And it will be a net force of 0 as it goes to the right, but we only care about the instantaneous moment after the collision. And that instantaneous moment after the collision, the velocity is going to be at a right angle to the bar, and the ball is the length of the bar away from the pivot point. So we can sub in here our 1/3 ml squared omega, and that has to equal, well, L in this case, where L is the length of the bar, not the angular momentum, times mv. And in this case, these two m's aren't the same. The mass of the ball is different than the mass of the bar, times sine of 90. Now, I don't have the mass of the ball present in the picture, so let's go back and get it, 25 grams. I'm noticing that the bar is just twice as heavy as the ball. Are you noticing that? So rather than put the number in, I feel happier just putting in a 2 here. Is that okay with you guys? Since the ball is just half the mass of the bar? I mean, I could put the 0.05 into 0.025 if you'd like, but this feels easier to me. Is that okay with you guys? You can say no. Well, no one said anything, so I keep going. These two L's are the same L, so I can cancel out one of the L's. And that leaves me with the velocity of the ball equals 2/3 times 1.5 times 4.5. How do I know this is right? The 1.5 is in meters, and the 4.5 is in radians per second. That's going to leave me an answer in meters per second. That seems very clearly like I'm on the right track. 2 times 1.5 is 3, and 3 divided by 3 is 1. So this velocity is just 4.5 meters per second. Consider not using your calculator when you don't have to. Your calculator lies to you because you tell it lies. You tell it things, you put it in there, you think the calculator is going to spit out the right answer, and often it doesn't. It is very... So our other example, we were looking at it from the side. I've taken the bar and I've set it down on a frictionless surface, and I've put the ball on a frictionless surface. And let's not even call it a ball. Let's say it's a puck. That way it's just sliding across this frictional surface. Everybody okay? Follow that so far? I want the ball to strike the rod, but the rod doesn't have a fixed pivot point. Everybody got it? Now, have you read your homework? How many of you have looked at the new homework? That's really not enough of you. You should jump on it. This problem is in there, and I ask you to try this problem a variety of different ways because there are a ton of different ways that this problem can be asked. It can be asked with a fixed pivot point for the rod. It can be asked where the ball sticks to the rod or when the ball doesn't stick to the rod. And then it can be all done again with no fixed pivot point for the rod, with the ball sticking to the rod or not sticking to the rod. Each one of these is a different problem and has real bizarre implications depending on how you're going to do it. The hardest version of this problem is the ball sticking to the rod with the rod not having a fixed pivot point. And for reasons I don't want to go into because it's pretty high level and I'm not sure you're there yet. So let's try this one. The ball strikes the rod, and after striking the rod is moving at 1 meter per second in the same direction. So we have this arrangement. So directly after the collision, the ball is still moving at 1 meter per second, but now the rod is moving. And I don't want to give it away, but if you don't know this going in, you're going to have trouble. The rod will have two forms of motion. This is a standard collision, so its momentum is going to change. And there was angular momentum before the collision, so its angular momentum is going to change. The rod will be spinning and moving at the same time. So this problem is tough. The only advantage about this problem is that there's nothing I have to deal with energy here, at least not yet. So let's take a look at how we would approach this problem. And just to be clear, after the collision, the rod's going to spin, so it's going to have an angular speed, something like that, but also its center of mass is going to be moving, so it's going to have a linear speed. So there's both forms of momentum at play here. Let's do the easy question first. In fact, why don't you do the easy question first? The easy question is a first semester problem where there is a linear collision between the ball and the rod. So find this first. Find the velocity of the center of mass of the rod after the collision. I'll give you a hint. It involves P equals P1 plus P2. Right? We've done this problem before. So, yeah, m times 4.5?
Yeah.
Great. What has momentum after the collision?
The ball and the rod.
The ball and the rod. But we're only talking about the linear portion of the momentum right now. So what's the momentum of the ball after the collision?
M times 1.
Yeah. It's traveling in the same direction. Be careful about the direction, guys. I didn't on purpose make the ball bounce backwards because I didn't want to add another wrinkle here. But if it had bounced backwards, that would be -1, correct? Keep in mind, velocity is a vector quantity. What do I have to do with the rod here?
Oh, the rod's doing, I put capital M times velocity.
Okay. I'm not going to put capital M because I know something about the mass of the rod. It's twice the mass of the ball. So I'm just going to put 2M if that's okay. And do we know the rod's velocity? No. So for that, we'll just put V. All right, that's it. I know you guys love to use your calculators, but cancel out all the M's. 4.5 minus 1 is 3.5. And 3.5 divided by 2 is 1.75. Yeah, this is not a calculator question. That'll be how fast the rod is moving. That's the center of mass of the rod. Now, the angular part's tougher here, guys. The angular part is tougher because we have to do the angular momentum of the ball before it strikes the rod. But the rod doesn't have a fixed pivot point. So here's where maybe some notes might be in order because there's some unique things that happen in this question. The momentum part, the linear momentum part, is pretty straightforward because we're only concerned with the center of mass and how it moves. In fact, a lot of people think that for whatever reason, that the rod's going to go like in that direction. But there was nothing with momentum in that direction before the collision, so there'll be nothing with momentum in this problem after the collision, which is why it just travels straight in the same direction that the ball was going. The next thing that's important here, and this is a little bit weirder, we don't know where the ball started. This is the thing we talked about when we first started talking about angular momentum for a point mass traveling in a straight line. So I'm going to, in my head, accelerate the ball or accelerate time until just before the collision. That way, I'll remind you that when we calculate the angular momentum of the ball, it's about the angular momentum of closest approach, the point just before contact. And just before contact, that is the direction the ball is traveling and where it strikes the rod. Does that make sense to all of you? Because the ball is going to have angular momentum, and that's R cross P, or R times P times the sine of an angle. And that's the angle between, it's hard to say torque arm, but it is a torque arm. The ball is applying a torque to the rod during this collision. There's an impulse. Now, here's the important detail. What's our point of reference? R has to have a point of reference, and that point of reference is critical in understanding what's happening here. We know the bar is going to rotate due to the action of the ball. So we need to figure out where the bar is rotating after the collision. That's our point of reference. That's not hard. Where's the bar going to rotate after the collision? Yeah, about its center of mass. Has to be about its center of mass because all objects, when free to rotate, rotate about their center of mass. This has no fixed pivot point, which means that the axis of rotation will be right about its center. So R is going to be measured from the center of mass. That's probably new to you guys. We've never done one like this. When we had our merry-go-round question, there's a fixed point of reference, right? Because it was the center of the merry-go-round. This one doesn't have a fixed point of reference. But we have to kind of interpret the fact that the bar is going to rotate after the collision, and therefore where it rotates determines what our point of reference will be. So that's going to be 1/2 of the length of the bar. Now, the ball has angular momentum both before and after the collision. We just figured out what we needed to be able to figure out the angular momentum of the ball after the collision, because it's continuing to move, so it still has angular momentum with reference to this point right here. Oops. This point right here. So after the collision and before the collision, the ball is going to have angular momentum. But the bar is also going to have angular momentum after the collision. And I think it's pretty clear, but I'll still, kind of talk about it. The angle is going to be 90 degrees here. And we were talking about the instantaneous moment after the collision, so it'll still be 90 degrees here. Even though the axis of rotation is moving, we don't care what happens after the collision, just the instantaneous moment after the collision. So in that moment, the bar hasn't begun to move yet. So I'm going to have 1/2 L as my value for R, mv as my angular momentum before the collision. Now the bar is just a bar rotated about its center. Be careful, it's rotated about its center. You're going to have to change the moment of inertia. So the moment of inertia will be 1/12. And I'm just going to put 2m there. Is that okay with you, Sam? I like that when the masses cancel out. And the bar's mass is twice the mass of the ball, so I'll just put 2m in there. And then I'll have omega for the bar. Don't know what that's going to be. This is just my I times omega. Plus, again, 1/2 L times m times 1. Now I'm going to stop for a minute.